Hello everyone, I welcome you all for this video session of Power Electronics series. So concentrating on inverters. So let us see the basic definition of inverter. So when you are defining an inverter is a static device which are having which are not having any moving parts, and the input of inverter consists a DC supply, and output of the inverter which will be given a variable voltage magnitude and frequency. So that means the basic objective of the inverter is it converts DC to AC with a variable magnitude and frequency. So it's nothing but an inverter. So when you are concentrating an input DC, the DC input power may be taken from a battery or it can be taken from a solar connected system. So let us see a basic example of a solar connected system. So here a solar connected panel we are considering. It is a 36 volts supplied to the DC to DC converter. The basic duty of the DC to DC converter, it can amplify the DC voltage from 36 volts to 400 volts. Now the 400 volt supply which is connected to the DC to AC inverter, so which converts the DC to AC, which 230 volts AC RMS value and 58 frequency. So as inverter not giving a pure sinusoidal wave, an output filter is connected to get a pure sinusoidal wave. This is the 230 volts 58. This is a simple block diagram which is controlled by one controller. So the duty of this inverter is whatever the DC supply available at the input of the terminals, that will be converted as a AC with a variable magnitude. We can vary the magnitude of this 230 volts and variable frequency. We can vary the frequency of the supply. So we will see the basic classification of inverters. The classification of inverters can be done on certain categories. The first category is that availability of whatever the number of phases it is generating. So it is classified into two categories. One is a single phase and three phase inverters. And based on the commutation, how you are doing a commutation methods. So one is the line commutation method. If you follow it, it's a line commutated inverter. If it is a forced commutation, then it is a forced commutated inverter. So based on the connection of thyristors configuration, so the category of inverters are three categories. One is a series inverter, parallel inverter and a bridge type inverter. And based on the nature of DC source feeding to the input to the inverter, so again the classification of this inverter can be done in two categories, that is the voltage source inverter VSI and current source inverter CSI. So this is the basic classification which we already done. Inverter module VSI and CSI. So once the VSI, we have the single phase and three phase. So in single phase we have the fixed voltage frequency, fixed variable voltage, variable frequency. So fixed voltage variable frequency we have the half bridge, again full bridge, again RLC, depends on load. And variable voltage variable frequency can be done with the PWM technique. So in three phase inverters, the operating modes are 180 degrees operating mode and 120 degrees operating. Similar thing will be there in CSI also. Now we'll see the basic model of single phase half bridge voltage source inverter. Single phase, only one phase will be available at output, and half bridge is the configuration model, and VSI is the voltage source inverter. The input type is input to that inverter is a voltage source. So here let us see the configuration of your half bridge voltage source inverter. There are the two sources connected with a center pointly connected load, and there are two switches T1 and T2 and the two diodes which are connected opposite direction to the switches. Now see the waveforms of this half bridge voltage source inverter. So here the Ig1 is the signal given to the T1 and Ig2 is the signal gate signal given to the T2. So when Ig1 signal is given T1, when Ig1 signal is T1 is given, then obviously the voltage is connected, the voltage is connected, the positive here, the voltage Vs2 is applied here, and the negative Vs2 Vs by 2 applied here. That means the voltage is positive applied across the load with this polarity when the T1 is triggered at time period of T by 2. So when the gate signal Ig2 is given to T2, then obviously the Vs2 Vs by 2 signal positive is given here and the negative is applied here, then a negative voltage Vs by 2 is applied here. So the output voltage is when T1 is triggered, the Vs by 2 voltage is applied at the half period. When the T2 is applied, so minus Vs by 2 is applied across the load. There are the two diodes which are connected. So these diodes can be helpful when the load is more inductive in nature. So we'll see the conditions of different cases of loads RLC conditions, so that the diode operation will be explained very clearly. So this is the voltage, output voltage. I have using first mode of operation, that T1 that thyristor T1 is triggered on, so that the Vs by 2 will be applied at the load. And second mode, that the switch T2 will be switched on, so that minus Vs by 2. When it is a load is a RLC load under damped condition. So under damped condition means, so the current is more forward than voltage. So current value is more forward, then that means the current is leading to the voltage. So this is the waveform of current when it is the RLC under damped circuit. So when you see the RLC under damped circuit, then here the current is 0 but voltage is positive. So up to this part, the current is this part, it is a diode D1 will be connected. And again, if you see this part, the current is 0, the current is positive and voltage is negative. Here again the conduction of diode will be takes place. So here the diode D1 will be takes place, and in this part of zone the diode D2 will be takes place. So the remaining part, if you see this zone from this 0 to this part, so the current is positive and the voltage is positive, so that thyristor T1 will be in the conducting mode. So here the diode D1 will be in the conducting mode, and thyristor T2 is conducting mode from here to here, and the diode D2 will be conducting from this part where the voltage is negative and current is positive. Similarly, when RLC load is the overdamped circuit, so overdamped circuit means the voltage is leading but current is lagging. You can see very clearly the current 0 becomes here, but the voltage is becomes 0 here. Current 0 here and voltage 0 here. So then you can very same thing will be happened here. When again this part, the current is negative and voltage is positive, the diode will be connected. From this part to this part, the thyristor 1 will be conducting, and here again the current is positive and voltage is negative, and the diode D will be connected. And this is the current nature when it is the RLC and overdamped circuit. When it is the RL load, the current lagging by the voltage, and similar thing will be happened. So diode will be connected this part up to this part, and thyristor T1 will be connected up to this part, and diode D2 will be connected up to this part. So and so it will be connected. When it is a pure inductive load, R load, so the voltage and current the current is completely follows the voltage. Where the current value is 0, the similar voltage value is also 0. So the current value follows the voltage. So we have the different load conditions explained in this waveform: R load, RL load, RLC overdamped circuit, RLC underdamped circuit. So let us see the basic analysis of single phase inverter. For any type of load, the output voltage waveform remains the same. Only the current waveform will be different. Just now we have seen the output voltage waveform is this one, but the current waveform is depends upon type of load connected. So the voltage RMS value, it is a 1 by T total time period 0 to T by 2 Vs square. Actually it is a Vs by 2 whole square, so we can make it Vs square by 4 dt plus T by 2 T is again the Vs square 4, because minus square will become again positive dt whole power 1 2. So this will give Vs by 2. So another form you can same thing we can mention like this, and the RMS value of the output, which is a Vs by 2. The fundamental RMS output voltage is V1 is equals to root 2 Vd by pi. It's a 0.45 of Vd. The total harmonic distortion of the output voltage waveform, it is a THD value is given. It is a 1 by fundamental value of the voltage to sigma. N is a number of harmonic number 357 up to infinite Vn square, which value is the 48.2 for half bridge inverter. The output voltage waveform for half wave is a symmetrical, because positive and negative is equal. So even harmonics are absent. So the average voltage is 0. The average voltage is 0. So the instantaneous value of voltage waveform can be represented notation with the Fourier series analysis. We can expand this. So n is equals to harmonic, odd harmonic up to infinite 2 Vs by n by sin omega t. So we can write the equation for I naught, which value is equals to 2 Vs by just Zn impedance. If you are deducted, then you will get a current. So your impedance Zn is equals to R square plus, so reactive component and reactive component square whole root. So phi of n is the angle is the tan inverse of your reactive component to the resistive component. So that is about the half bridge inverter. Now we will go for a single phase full bridge inverter. So full bridge inverter consists the 4 controlled switches and 4 diodes, and the load is connected between P and Q, and one source is connected to that path. Now full bridge inverter when conducts load voltage, and when load voltage is frequency, the output voltage can be controlled by varying the periodic time. So diode are called, whatever the diodes connected, which are called the feedback diodes, they function only when the load is diodes are called feedback diodes. Their function is only and the load is other than resistive load, more inductive load conditions. So these diodes are feedback diodes. They can connect only power is negative and source is positive, like this. So you can see the waveform of full bridge inverter. So when G1 and G2, the switches G1, the switch G1 and G2, when at a time the switch G1 and G2 will be connected, when G1 and G2 is connected, so the voltage appeared across this load is Vs. So the voltage applied across the output is Vs. So similarly, when G3 and G4 is on, the negative voltage is applied across the load. So the output voltage will be plus Vs minus Vs, whereas in half bridge we will get a minus plus Vs by 2 minus Vs by 2, but whereas in full bridge inverter, so we will get a full voltage Vs in positive half cycle and minus Vs in negative half cycle. We can see at different loaded condition what is the current. So as we have now seen, the voltage is the plus Vs and minus Vs. When it is a pure resistive load, then your current follows the voltage. When it is only inductive load, the current is lagging by voltage, so current value makes 0 here. So before that, the diodes will conduct, the diodes will share the current. Once the switches are triggered on, the positive current and positive voltage will be there. When the T1 and T2 is switched off, then the T3, T4 are not switched on here. So the D3 and D4 will conduct here. So here this current will be shared by your D3 and D4. So at this point of period, your switch T3 and T4 will be switched on, so that your voltage and current both are negative. So again the process will be repeated. D1 and D2 will share the current up to the part when the T1 and T2 will be conducting. Similarly, when RL load, there will be some little bit change. So when RLC overdamped condition means, so it's the value of voltage 0.0 is leading by compared to current. So that in this period the D1 D2 will be conducting. When the current will become positive and voltage will become positive, T1 and T2 will be triggered on. So similarly up to this part it will be there. When voltage is negative and current is positive, D3 and D4 will be conducting here. So similarly process will be continued next cycles also. When RLC is a underdamped condition, the current is leading by the voltage. So current point will be 0. It will be leaded by some part with respect to the voltage. So similar thing will be happen because the current is positive and voltage is positive. So T1 and T2 will be connecting here. So when the current will become 0 and the voltage positive, here the current will become negative. So this part, negative part of the current is shared by D1 and D2. Similarly up to this part, so when the current is negative and voltage is also negative, then T3 and T4 shares the current, load current. Similar process will be continued. So this is the load current, different loads and different load currents with respect to load change. So as you just now we have seen in mode 1, the switch 1 and switch 2 will be on. So when this is on, current is positive and voltage is also positive. In mode 2, when T1 and T2 are switched off, T1 and T2 is switched off, then your diodes will be conducting. So then obviously current is positive but voltage will become negative. Similarly, mode 3, switch 3 and switch 4 is conducting. So the negative voltage is appeared across this and negative current will be appeared across this. Now once the T3 and T4 is switched on, D1 and D2 will conduct and negative current and positive voltage is appeared across this one. So the forced combination is not required for these switches because the current value is becoming 0 at each and every cycle. So forced combination is not required, only load combination or natural combination will be happened in your full bridge inverters. So the RMS value of this one full bridge inverter, it is a Vs, whereas for half bridge inverter it is a Vs by 2. A simple simulation full bridge inverter which is implemented on MATLAB, so we can see the 4 switches we have connected as a bridge model, and a DC source we have connected, and a getting signals we have connected to gate signal, and here the diodes are not connected, the diodes are inbuilt in the circuit in the switch. So when T1 and T2 properly designed your gating signals and T1 and T2 is on, so the output voltage is a positive off cycle. So when the T1 and T2 is off and T3 and T4 is on, the output voltage appear across the load is negative Vs.